Okay, you got that? Are these new words or words you might know? Yeah, we've heard of these terms before perhaps. Okay. From chemistry, or even basic science, you know that electric charge is a basic property of electrons and protons and other particles. We say electrons are negatively charged and protons we say are positively charged. And I hope you all know this already. Things that are negatively charged and things that are positively charged pull on each other. This is what makes the electron and the proton stick together. But things that have the same charge push away. They repel. And we call this the law of charges. Now, have you done this in chemistry? Yet? Yeah, no, I just mean this year.
Yeah, I guess so.
Well, I mean, has Lorraine mentioned that electrons and protons repel or attract?
Yeah, I guess we will assume to have known this.
I would hope so.
Yeah.
I would hope so. Can we don't need to write all of this down, but do you all know these words attract and repel?
Yeah.
Yeah. So you could at least write down that, you know, attract and repel and law of charges, just so you can have that vocabulary. Opposites attract, do they? Yes.
Unless they monopoles.
They don't exist.
Not yet.
Not yet. I mean, people have been looking for a while. They haven't found any monopoles yet. Okay. We got that? Yep. Now, has Lorraine talked about current or anything like that? Probably not. Doesn't really come up in chemistry.
Well,
Conducting, okay, fine, yeah. So, an electric current is a flow of electric charge. Well, that's a fairly simple definition, so we can get that down. Okay, you got that? Yeah? Now, in a metal, it is free electrons that flow. So you would have learned from Lorraine that metals, conductors, are full of free electrons. These are electrons not, what's the word, bound? Delocalized electrons, free electrons, yeah? That flow. And here's a very simple picture. So you have a copper wire, and it's the electrons that flow through the wire. The electrons have a negative charge, so this flow of negative charge is a flow of current. It's a current flow. So it's a very simple picture, but it'd be nice to add that to your definition, please. Yeah, I think so. For most things, yeah. What? Yeah, yeah. I think so. Okay, you got that? Yeah? Now, does anybody know what an electrolyte is?
Charged atom molecule.
No, it's this
No. Yeah?
electrolyte is as in solution or
It's a
something
liquid.
liquid where electricity where electrons can
With charged particles.
or
Mm,
it can charge something.
close, close. An electrolyte is a chemical, usually a liquid. Although I suppose it doesn't have to be. It's usually a liquid that conducts electrical current. It's used. So this is what you were getting at, Dorian. It's used in batteries, but it's not electrons that flow. It's ions that flow that produce a current. Oh, you know what ions are, don't you? I don't need to write that down. You all know ions, I would hope. Otherwise, Lorraine will kill you if you don't.
Ions are opposite of ions.
They're opposite of what?
Ions.
Yeah, indeed. Oh dear. Okay, you got that? You all got that? Yeah? You know what ions are. And here's a picture of an electrolyte. We don't need this in the exam. It's a simple battery. You could put some zinc and copper into this H2SO4. Yeah, yeah. Yeah, that's all. We don't need that. Okay, so which way should we say the current flows? So here's a picture. Do we say the current flows from positive to negative? From negative to positive? What do we think?
Are we talking conventional
Well, you tell me.
or how it actually is?
Which? What's the difference?
One is how it
Positive to negative? Maybe.
conventional is positive to negative.
Yeah. See, there's a problem here. It's both. So, as Zach was saying, positive to negative is what's called the conventional current. But the electrons are actually moving from negative to positive. This is the electron flow, which is a bit of a pain. So yes, we say the current goes from positive to negative, but we say the electrons go from negative to positive. So conventional is positive to negative, and electrons are negative to positive. So you have to be very careful with that. Maybe you could draw this too. Got that? Yeah. Got that, Gina? Yeah. So, just to be clear, if an electron moves from A to B, We say there's a current flowing from B to A. That's right, B to A, even though the electron is flowing from A to B. Are you clear on that point? Dorian, yeah? Yeah? Okay, okay. Why, you might ask, for this ridiculous situation? Well, the reason is because we called electrons negative and protons positive. It would have been better if it was the other way around. Now you might be saying, how could it be the other way around? Of course it can be the other way around. Think about it like this. Which hand is this, left or right? This one here? Left. And this one here? Right. If tomorrow we all swapped and called this one left and this one right, there'd be no problem. There's nothing leftness about this or rightness about this. Do you understand? It's just a naming convention. The reason we call electrons negative and protons positive isn't because an electron really is negative and a proton really is positive. It's only because they're opposite, like left and right. So, it would have been much better if electrons were called positive and protons were called negative. This is the reason we have this problem. Okay? Why is it like this? Benjamin Franklin, the fellow with the kite in the thunderstorm, in his experiments he called the current that was left on the glass, he called it positive. It would have been better if he called it negative. He didn't know that it was a proton that was left behind in the glass. So anyways, long story short, we called them positive and negative before we realised it would be better the other way, and now it's too late. So that's the way it goes. Okay, so now we have to give the definition of an amp. Now I'm very sorry, this definition is probably the hardest definition in the course for 1 amp. 1 amp is how we measure current. You might have heard of an amp before. You would see it on the plugs. Okay, 1 amp of current is the amount of current that will produce an attractive force of 2 times 10 to the 7 minus newtons per meter between 2 straight parallel conductors of infinite length and negligible area 1 meter apart in a vacuum. So, if you have 2 conductors and they're 1 meter apart and they both carry 1 amp and there's an attraction between them of 2 times 10 to the minus 7 newtons, then you know you have 1 amp of current. This is a terribly difficult definition. It's a terribly difficult definition that has been on the exam once in the last 12 years. You've got to, yeah. You should be. What's this? Well, you don't have to understand why there's an attractive force yet. You just need to know that this is the definition. You just need to accept it as a fact for the moment that there will be an attraction between these 2 currents. Okay, write that definition down carefully.
That's what I was thinking.
It's a mathematical reason to make constants work out later. It's an example of making the definition a certain way because you want the answer to be a certain way later, you know.
Wasn't there any other way to measure electricity?
No, just amps, no.
How else would you measure electrons moving?
Yeah.
Watch them, it's like watching Formula 1 through a microscope.
No, it's not. Electrons move shockingly slowly in a conductor. if you can believe that. They move at a rate of about millimeter per second. This is a common misconception people have. They're picturing the electrons zipping through the conductor. But you need to think of them more like an army of electrons slowly marching in large numbers through the conductor. How do I do reply all? I've got a meeting today. But I want to get fish and chips.
Where's the fish and chips place?
I don't know, Sylvia's going to order some on Uber Eats, I think.
Did you use your code?
No, not yet. I was trying to use it this morning, but I couldn't make an account. I couldn't get the code. Anyways, do you have that?
Conductors of negligible resistance as well.
Not part of the definition officially, and it's already a long enough definition. I think the negligible cross-sectional area amounts to saying the same thing as negligible resistance. Okay. Oh. Let me know when you're ready, Diego.
Yeah.
You are? Oh, a bit. I'm not used to my smartphone. Right. Next. So the Coulomb. Does anyone know what the Coulomb measures? No, you've not?
Coulomb is,
Coulomb?
resistance.
No.
Charge.
No. Anyone knows what Coulomb measures?
Current.
No, Zach, we just said the amp measures the current. Charge, thank you. See, this lesson was called Current and Charge, and we already covered current, so it has to be charge. The Coulomb, symbol C, is the unit for measuring charge. What is the definition? It's the charge transported by a current of 1 amp in 1 second. So, this guy here, you have 1 amp for 1 second, then the total charge that you get out is a Coulomb. So, that's a pretty simple definition. And that can give you this nice little formula, that the total charge, Q, is equal to the current multiplied by the time. Where Q is total charge, I is current, and delta T is time. You got that? Yeah? Yeah? Continue? Yes? How big is 1 Coulomb of charge? It's actually pretty big. A Coulomb is a lot of charge. So quite often we find that we're measuring charge in millicoulombs. Let me show you how big a Coulomb is. 1 electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. So you have a lot of electrons if you have a Coulomb of negative charge. And often we just write that as minus E for short. Or in chemistry class you might even just write it as quote minus 1 charge. I think I would like you to make note of this fact, please.
So we write like H plus. It's not actually plus 1.
Well, plus 1 just for short, but really you're measuring in coulombs, so it's a plus E. E representing that number.
1.6
Yeah.
plus 10 to the minus
Yeah.
19.
Not to be confused with the E in maths class. Right? Of 2.718. Continue. Continue. Yeah? Yeah?
How many electrons in the Coulomb of charge?
Oh, just get the reciprocal of this number and you have the answer. Alright. Next. Here is a super simple question. Sorry. Here's a super simple question for you. 100 milliamps flows for 2 seconds. What is the total charge? 'Tis not. 'Tis not, is it?
What?
Why is it not, Dorian? It is not 200.
It's milliamps.
Yeah. Hmm?
Milli
No, it
is
is 100.
2 minus 3.
Yeah. What's the answer, Dorian?
100.
No. What is it?
0.2.
0.2, yeah. 0.2 coulombs.
Okay.
Okay? Are you sure? Are you? Okay. There's another question I want to do, which I actually have in my bag. It's a question I like. Let me see. Let me see. Where the heck's gone? Ah, here we go. Okay. Now, next question. Now, this is a hard question, but I like it. Copper is used to form a wire. So what I have here is I have a copper wire. Let me draw it. It's already terrible. Okay, copper wire. And I will make the diameter 2 millimeters. And the length, I'll make it 1 meter. And I'll also make the density of copper.
Great scales.
I'll make the density of copper 8,940 kilograms per meter cubed. I'll also make the molar mass 63.5 grams, and I'll have a current here of 1 amp. And also I tell you that copper has 1 free electron per atom. And I'll also, I don't think I have to give you that. Okay. So are we okay with the picture? I have a copper wire, I have 1 amp of current, and my question is, how fast are the electrons flowing? How fast are the electrons moving? That's my question. Now, we'll do this one together. What should I do first, though? Okay, we can find the area, but even more important, I think, is to convert 1 amp, remember from the definition, is 1 Coulomb per second, right? It would be good to know how many electrons that is. So the number of electrons would equal 1 over that E value I gave you a minute ago. So can someone type that in and tell me what you get?
1.6 times 10 to the minus
19, yeah, wasn't it?
6.25 times 10 to the 18.
10 to the 18. Okay, yeah? Now, we need this many electrons per second. Okay? So, what we'll do next is we'll work out how many electrons we actually have. Then we can know how fast they need to be going. Okay? So, just before we continue, maybe we don't need all the electrons to leave in 1 second. Maybe that'll be too much. Or maybe it's not enough. You know, but first we should work out how many electrons we have in the copper wire that are free. Okay? So let's see. How many moles of copper do I have? I have the density of copper, don't I? So let's get the mass of the copper. That is density by volume, isn't it? So that will be 8940 times pi r squared times 1 times 10 to the minus 3 squared. So 10 to the minus 6. So that's, the r is 1, sorry, so that's gone. Sorry. So it's just going to be 8940 pi times 10 to the minus 6. To 8. So that's 28 grams, isn't it? Yes?
Yeah.
So if you divide that by 63.5, we can know how many moles there are. So just divide that by 63.5. Do you know what that is? That's my Uber text. Because I tried 10 times to make the account this morning, so I'm going to get 10 confirmation codes now. Still a few more coming. Yeah.
4.42 times 10 to the minus 4.
What? No, 28 divided by 63.5.
Oh. Still in kilograms. 0.44.
0.44 moles. Now, how can we work out the number of atoms of copper? Time Avogadro. And remember, I said each atom, there should be 1 free electron in the copper. So if you multiply this by Avogadro, we'll get the number of free electrons.
2.66 times 10 to the 23.
Yeah? You got that? Yeah? Now look at what we have. We have many, 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 many more electrons than we need in a second, right? So, for example, if I zoom out here, if each of these electrons were moving at 1 meter per second, then you'd be guaranteed that all of them would exit in a second. But that is way too many, isn't it? Like it's like 10,000 times too many, right? So what proportion of the electrons do we need to exit? Not all of them. If we take this number and divide by this number, we can get the proportion of electrons we need to exit. Okay? So can somebody do this divided by this and we can get the proportion that need to exit? The proportion to exit is 0.
2.35 times 10 to the minus 12.
Okay, so 1, 2, 3, 4, 2, 3, you said, was it?
Yeah.
2, 3, 5?
Yeah. Yeah, 4 cents.
Okay, well, roughly, right. So that means you only need like a tiny little bit here. This proportion. Yeah? Now, I kept it easy because this is 1 meter. It means you just need this many, this much of the wire, this little piece here, these electrons to exit at the very end. Okay? So you can get the speed now by saying speed is distance over time. And again, what's the time here? 1 second. So that's just going to be 0.0000235 meters per second. 1, 2, 3, 4, 5.
2.35 times 10 to the minus 5.
Yeah, so that will be 23.5 micrometers per second. Yeah. Yeah.
Micro is 10 to the power
Minus 6. Those are slow-moving electrons, but it's enough to make 1 amp.
Well, relative to the size, it's pretty
Well, I suppose relative to their size, it's pretty fast. Relative to the person using the current, not so fast. Question, Gina? You don't look happy with this.
How did it get to the number of electrons?
Yeah, it was this number here multiplied by Avogadro. Yeah. Anything else? Is that yes, no? Anything else?
something like the ratio.
Can I close this?
Yeah.
Don't. That's an advanced question. The questions I give you from the exam, they're not that advanced. Like, how many do I even give you there?
Two. Three.
Okay, wow. You'll,
Full theory. The most.
any calculations?
Yeah, there is. This, yeah, Nathan is it.
No, don't say that. Let me have a look. Sorry, can I have a look?
Question 3.
Oh. Oh, yeah, well, just it's the last part of 3, isn't it?
Yeah, B and C.
Yeah, number 3 maybe is a little too hard for you, but you can certainly do number 1 and 2. Okay, so can you try number 1 and 2 now, please? Thank you.